Yeah, how about the cats? Fascinating.
This one of the
And
big
even as soon as you decide,
Yeah.
yeah, we're like asking.
Well then people who go
Yeah,
like
together with cereal boxes,
well also
stable
these
bearings,
yeah you were
school rollers, like
PTFE
PTFE2
salt. Yeah, he was just like, he was like, what do you mean you can't?
He was talking about like
No,
the
everyone has to
it is
Yeah.
like fails.
Yeah.
Like some feature failed.
like 7:30, bro. And didn't make a PTFE long enough.
And then the engineering drawing, four points. Are the three rules. Dimensions are scaled to specify. Hidden features shown as like thumbs.
Wait, they
And then title block is what? Make sure to submit the ST.
I don't know, but like
Yeah.
just one down to five.
that's
Yeah.
See,
that's not gonna work for me then.
Mine's the opposite. I can do it before.
Besides against grade school, oh yeah, you have to do the app.
My girl. I don't wanna make
Give it a shot.
Like the stupid Aussie keys, like my keychain. It doesn't matter DLA, but the things that go on unlock the shopping carts and all these, I don't have to remember.
Today, I will give you a hint about how to approach homework 2. I hope all of you successfully submit your homework 1. Okay. So, last session, I drive for you this equation for drag force. Okay, this is an equation for the drag force. This equation is accurate. Let me write over the board that airfoil in control volume. General relation if pressure equal P infinity over all boundaries. If pressure is equal P infinity over all boundaries, if upper and lower, this is 1. This is 2. If upper and lower boundaries are a streamline. One simplifies to So, for your homework too, you can use this equation, but this equation is not entire story. Why this equation is not entire story in homework too? Yeah.
It's only the outlet.
What else we have?
We don't have P infinity at all boundaries.
Yeah, we have P, a distribution for P at infinity. Here we ignored P effect. Okay? P or it is the assumption. Okay? 3. If P not equal P infinity on outlet. Your homework too. So what your homework too is the question I gave to my student in Embry-Riddle in their midterm 1. So I give the midterm exam question as a homework in the next semester. Okay, what we should do? Follow me and take a look at the board. It is very important. It is our boundary, it is our control volume, P infinity, P infinity, P infinity, P, Y. What I do for this control volume? Now take a look here. From all 4 surfaces, I reduce P infinity. I make P infinity reduce it from P from all the 4 surfaces. How much is P here?
P infinity.
No, after I reduce P infinity. 0. Here. 0. Here. 0. Here. Py minus P infinity. Okay? So the pressure term only appears for surface exit outlet. So drag due to pressure, is Py total drag viscous plus drag pressure equal Okay? This is the story. This is the story. If you may ask me why did I reduce P infinity from P of all surfaces? Yeah?
Is it because they can cancel each other out?
If I don't do that, what happened? What should I do? If I don't reduce P infinity, my word becomes very complex. Why? Why, if I don't reduce P infinity from all the surfaces, my word becomes, yeah?
Is it because you have to deal with streamlines?
Because I need to integrate P infinity here, P infinity here, P infinity here. I need 4 integrals. Now I need 1 integral. Okay? I need just 1 integral. Otherwise, I need 4 integrals. Okay? So for your homework, it has 2 terms. But please double check the sign of this one. I assume the sign should be positive, but double check. The sign, I think the sign should be positive. Maybe it is negative. I'm not sure here. I have here, let's see what, I don't have pressure on sample that I bring for you, doesn't have pressure. In Embry-Riddle, I didn't tell the student this. And in the exam, I asked them this question. And yeah, but for you, I told you to tell you, and then you had a easier job. Now, let's go to continue our discussion. Let's back to this one. So far, what did we do so far? So far, we derived for you continuity equation. We derived for you momentum equation. And then we saw the application of momentum equation in aerodynamics. Okay? The application can be in any problem. The application can be in any problem. And one question, I'm not sure if I ask you to compute the lift of this airfoil or no. Lift is equal P lower minus P upper dx. Okay? How much is lift for this airfoil? 0, because P lower is equal P upper. P lower is equal P upper. But if I give a distribution for pressure on different on the bottom and different on the top, we will have lift. Okay? For example, if I give a distribution of pressure here, different from there, there will be lift. So we consider momentum equation, and the art of mechanical and aerospace engineering is to use this complex integral to relate this integral to a real world problem. So I didn't derive for you any relation for lift or drag. I didn't give you a closed form relation for drag, but you can compute drag from this relation. You just go to a wind tunnel and measure the velocity at the inlet and at the outlet, and then measure the drag. Measure pressure at the inlet and the outlet, you can measure the pressure drag. Okay, so it is the application of governing equation. We are engineers, we are not physics students. Physics student may read, okay, just go to a molecular nature or what happened, derive the equation. Derive the basic equation. We don't want the equation for themselves. We want the equation for an application. And this is our aerospace application. Okay, now we go to the flow similarity. You know that from fluid dynamics, that in the specific case of aerospace problem, you have a very big airplane, but you cannot test that airplane in a small wind tunnel. You you build a model of the airplane and build a model in the wind tunnel, but keep Reynolds number, Mach number, and angle of attack the same between the big one and a small one. So it is all a story. So the student who have intro to flight class with me, I told them I visited fluid dynamic laboratory in ETH. ETH is which country it is? Switzerland. It's very, very famous university, very old university. Instead of wind tunnel, they tested the airfoils of wind turbines in water tunnel. Why? Because I told you Reynolds of the real object should be Reynolds of model. Okay? In order to test and get the same coefficient of force, the Reynolds on the real, it is the real, it is the model. Okay? It is the real wind turbine airfoil, it is the model turbine airfoil. Reynolds should be the same. What is the definition of Reynolds? Reynolds is rho u L over mu. This is L, this is L prime. Should be rho prime, u prime, L prime, mu prime. Prime is the model, without prime is the real. Okay? Which L is a smaller, L or L prime? L prime is a smaller. So I put it air, I put it water. Okay? How much is rho of air? 1. 1.25, I assume 1. 1 multiply U multiply L over mu. What is the mu of air? 10 minus power 5 or 4? I take minus 5. Should be 1000 U prime. I take L prime 1 over 100 of L. Ten power minus 4. So, because L prime is 1/100th of L, I increase the density from 1 to 1000. Okay? I increase the density to compensate the equation. So 10 power 5 UL is equal 10 power 5 U prime L. So U is equal U prime. I can create the same velocity on both objects. So you can test a wind turbine in a water tunnel. Why you should do so? Because you keep the Reynolds the same. Otherwise, if I use rho of air, if I model the small object in the water wind tunnel, I need very high velocity. And the flow may have some shocks, something that make it totally different. Okay, now let's go to different type of flow over airfoil. The flow over airfoil can be categorized based on Reynolds number and Mach number, okay? Both Reynolds number and Mach number. If the Reynolds number is very, very low, between 0 to 100, the flow is called to be in creep condition. The low Reynolds number, in order to memorize the low Reynolds number flow, consider honey. Honey is a very low Reynolds number flow. It doesn't, when you put honey in a spoon and then you incline this, you make the spoon in this way, the honey moves very difficult, very slowly. It is the creeping flow. So I told you I taught a course in Johns Hopkins. A very good amount I taught speaking about the creeping flow. Creeping flow are specified by very high drag force. Why the drag force is high? Take a look at Reynolds. When the creeping flow is a small Reynolds flow. When this is a small, either mu is high or u is a small, okay? In any case, it is a flow that the denominator is considerable. Denominator is considerable. So viscous force is important. So it is very high viscous drag. It is not, it doesn't have pressure drag, okay? This flow doesn't have pressure drag. Mostly has viscous drag because the viscous force is very high. So creeping flow, viscous effect dominates, drag inversely proportional to 1 over Reynolds. CD is proportional or 1 over Reynolds. So CD is like this. CD Reynolds. So in Johns Hopkins, I give the student a project to simulate flow over a sphere at low Reynolds number with fluent, open foam, console, something like that. And they did so, and also over a block, rectangular or a square block. They simulated flow around the square block. And then I put the nicest picture of them, I put in my book that published last year, because in my book I discuss about creeping flow. In microfluidics, we have creeping flow. So I put the nicest figure, the vortices behind the sphere, behind the block in my book, a very nice picture. And I mentioned the name of the student. In the caption of the book, I wrote, this is from a student, blah, 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 from Johns Hopkins that prepared this homework, these figures. Okay, so it is creeping flow. So if you in airfoils, we don't have very low Reynolds number unless you have a very, very small and the size of insect. If you have a drone at the size of insect, because Reynolds number, because air, mu of air is 10 power minus 5, okay? So Reynolds at least is 10 power 5. It is on the denominator, 10 minus 5 on the, let me write here. You should have a feeling of Reynolds number, okay? Rho UL over mu. Rho of air, one airfoil work in air. Assume your airfoil is super slow and rotate or move with 1 meter per second. Then it is 10 power minus 5. So your Reynolds is 10 power 5 L. Okay? So if your airfoil cord, L is the cord of the airfoil. If your airfoil cord is at the size of 1 micrometer, Reynolds is equal 0.1. Creeping flow. So if your length is very, very small, if you have a micro airfoil, the airfoil should be at the thickness, not length of your hair. If the airfoil thickness is at the same as your hair's thickness, you are in creeping flow. So it is for spying. So maybe it comes to this room, take a seat and record us. Okay, it is for that. It is not very practical. So, but for the cylinder flow, it may be somehow practical. But for airfoil, no. And interestingly, there are a lot of analytical solutions for this regime for a sphere. In my course, I taught a lot about the analytical relation for creeping. Then we go to the Reynolds 10 power 2, 10 power 4. We have a low Reynolds number, laminar flow. We have vortex shedding. Behind the airfoil, we have vortex shedding. Separation bubble. There is a separation bubble behind. Reduced lift drag proportional to Reynolds. So this is more physical. So you have this airfoil, Reynolds 10 power 4, and flow approaches. I intentionally plot a small airfoil because this airfoil should also be a small. And then you have vortex shedding. A lot of vortex are shed behind this airfoil. And also a separation bubble. What is separation bubble? It is our airfoil. The flow comes here, and at some point it starts separating. When it starts separating, a region of vortices appear over the airfoil, and after that the flow separates. This region is called separation bubble. It is not a bubble, but its shape is like a bubble. This is called low Reynolds laminar. Then we have laminar flow between 10 power 4, 10 power 5. Again, we have separation bubble, decreased skin friction, earlier separation, earlier stall. Pay attention. Laminar flow is not a good flow for aircraft. Why it is not a good flow? Yeah?
Because the vortices don't create lift, or like, it's just streamlined.
In terms of separation.
Yeah.
Yeah, you. Turbulent also has drag. Both laminar and turbulent both has drag. Yeah?
Turbulent flow like sticks to the surface better and it's
Is-
less it sticks to
Yeah.
the surface better.
Yeah, yeah. turbulent, we have laminar, turbulent. It is very important to distinguish these two. This is the separation bubble. This is separation bubble and flow separate. Question 1. Which of these two flow has higher, which flow is like this? Which flow is like this? This is laminar or turbulent? Laminar. This is laminar or turbulent? Turbulent. So, laminar flows are layered flow. Near the surface, the velocity is very small boundary layer. As we go up, the flow has higher velocity and higher energy. But higher energy here is not transferred to low energy here. Why the energy here is not transferred to here? In the laminar flow, yeah?
Because no vortices, so I kind of mix the
Yeah.
higher connector.
Because the flow are like separate layers. So this flow is can be very easily separated. So laminar flow can very easily separated. Laminar flow are people that don't support each other. I move my way, you move your way, you move your way, and we don't take our hand together. So if I go right, I go right. No person help me to back to the original, to the airfoil. Okay? It is laminar. But turbulent flow are people that are rotating, moving. If I am going right, if people hit my shoulder and I may return back to my original direction. It is a turbulent flow. So turbulent flow has a natural mixture, natural mixing, natural anti-separation property. But pay attention. Turbulent flow, higher friction drag, higher CF, friction drag, lower CF, lower friction drag. This has higher friction drag, lower CF. But earlier separation, lower C D pressure, higher CD pressure. Turbulent flow, higher CF, late separation, lower CD pressure. So, airfoils are So airfoils are better or aircraft are better to work in turbulent region. Over the surface of the wing, we have vortex generators that make the wing flow to become turbulent and more chaotic and more resistant to separation, okay? More resistant to separation. This is more dangerous. This is more dangerous than higher CF. CF is the friction drag. We can create more thrust. But when the flow separates, we have a stall, much less lift, and the aircraft crash. So we should work in turbulent region. Transitional between 10 power 5, 10 power 6, both laminar and turbulent boundary layer with characteristic of transitional means that your airfoil here is laminar, here is turbulent. It is the transitional flow. We have both regime on the same airfoil. Most of the airfoils in practice are in transitional, but we want that transitions occurs very soon, not very late, not very near the end, just at the beginning. And turbulent Reynolds greater than 10 power 6, inertial effect dominate. Pay attention, Reynolds 10 power 6. So the numerator is much greater than the denominator. So the flow is mostly affected by inertial force, increased skin friction, I wrote you here, higher CF, delayed separation, I plotted for you in the figure, delayed stall, later stall. In airplanes, we want to avoid a stall. Okay? Let's go to the Mach regime. So, if Mach number between 0 to 0.8, the flow doesn't have any shock. The flow is shockless. No shock. But if Mach number between 0.8 to 1.2, here it wrote not 1.6. So sorry. Let me describe this. If Mach number is 0.8, the flow approaches the airfoil, and over the airfoil, flow accelerates. When the flow accelerates, it reaches Mach 1. It accelerates more, Mach 1.1, 1.2. But as the area starts increasing over the airfoil, the speed should goes down. The speed should goes down. In that case, there is a shock. There is a lambda shock over the airfoil that terminate the supersonic regime. That terminate the supersonic regime. So it is called transonic flow. We have region of subsonic, region of supersonic, region of subsonic. Again, this is called transonic flow. Mach number 1.1, there is a bow shock in front of the airfoil and some oblique shock at the end. Okay, so when the flow is slightly supersonic, this flow is slightly supersonic. There is a detached shock in front of the airfoil. Behind it, the flow is subsonic. Then flow accelerate to supersonic. Then again, two shocks return the flow to subsonic. We have four kind of shocks. This is normal shock. This is oblique shock. This is lambda shock. This is bow shock. Types of shock. We have four types of shock. The student who has class on propulsion, I think in the propulsion class, they will become familiar with the different types of shock and the flow properties before and after shocks. I give you a minute to write. So, is there any question on different, yeah?
Yeah, in your diagram showing bow shock and oblique shock, why is M, the Mach number at the end, less than 1?
Because there is a, okay, it can be greater than 1, yeah. Yeah, you are right, it should be greater than 1. Yeah, it should be good because it's oblique shock, but it is. Smaller than Mach 1. Yeah. So, the researchers, if you remember, Wright brothers and the evolution of the airfoils, use this type of airfoils. But this type of airfoils are not good for supersonic flight. For supersonic flight, these are not good at all, okay? Because there is a bow shock, and the shock increases the drag a lot. Previously, I told you we have two types of drag, friction drag and pressure drag. Now I should add we had another type of drag called wave drag, drag due to shocks. So CD is equal CD friction plus CD pressure plus CD wave shocks. Separation, friction. So it is for high speed flow, we have additional drag due to the waves that can result in higher drag of the airfoil. This higher drag is challenging, is not good. So the people don't use, if you have a fighter, the student who came with me to the aerospace, New England Aerospace Museum, we saw the fighters. The fighters don't use this airfoils like NACA airfoils. They use it very thin airfoils like diamond. These airfoils. Very simple airfoil. This is M greater than, for example, 1.8. There are two oblique shock here and expansion waves here. Expansion waves here. Expansion waves increase the velocity. Shock decrease the velocity. Expansion waves plotted at the middle increase the velocity. I know AIAA Club has another visit. Where you go? AIAA Club have a visit to a Pratt and Whitney.
Yes, we're going this Friday.
What is it? Is the just for engine?
I think they just said we're seeing the general like mechanical engineering area.
Okay.
They didn't really
Yeah.
specify what exactly. we're gonna
Okay.
see.
Yeah. So the student go to another visit to Pratt and Whitney. So it is very good if you have extra seat and anyone is interested, you can contact Trinity and AIAA Club for going to the Pratt and Whitney. So yeah, when you go to visit, you can take a look for something that you learn to visit it, to watch it to see it in the reality. So when we go to the supersonic flight, we use these airfoils. We don't use NACA airfoils. NACA is just for subsonic, not transonic. Even for transonic, there are a specific type of NACA. For supersonic, we use diamond or triangle, half triangle airfoils. Okay, and for hypersonic flight, if it is much higher, we have different type of much thinner airfoils. Let's go to the conservation of energy or last equation. Our last equation is conservation of energy. Conservation of energy, as you see in equation 1, 2, 2, says that change in energy is equal work done on the system plus heat transfer to the system. So change in energy, dE, is equal dW plus dQ. Work plus heat transfer. Work and heat transfer change energy. Okay? This is all the story about, it is the first law of thermodynamics. First law of thermodynamics, but we write it in an fluid dynamic manner, like the conservation, like the momentum, transport of momentum equation. We write it in a fluid dynamic manner. Now we write this equation in a fluid dynamic manner. So, continuity this continuity. Continuity says rate of change of mass in the control volume plus mass transfer through the surfaces is 0. Energy equation says rate of change of energy inside the control volume plus energy transfer through the surfaces, door and windows, is equal work plus heat transfer. Energy has two parts, internal energy and kinetic energy. Your work consider also potential energy, so I can add a potential energy, rho g. Rho g z. But for gases, rho g z is negligible. So energy has three parts. Internal energy. I shouldn't put rho because rho we have already and rho outside the parentheses. We have a rho here outside the parentheses. So it is E. Energy has three components. Internal energy, small e. Small e is equal, what is the relation between small e and temperature? Yeah?
dt.
No. Small e and temperature. Internal energy and temperature. Yeah?
It's a direct relationship. As temp goes up, internal energy goes up.
Yeah, what is the mathematical relation? The math relation, E is equal CVT, okay? H is equal CPT. Let's work on energy equation in this room. Why did I open the door and open the window? Why did I open door and window? You?
It's hot in here.
Say again.
It's hot in here.
You?
Because the rate of mass into the control volume has to be equal to the rate it goes out.
No. I don't want to transfer mass today. I had another goal by opening this door. Yeah,
To transfer energy?
transfer energy. Yeah. I was hot. Okay, I was very warm. Today is very warm in this room. Here the room temperature is very hot. Okay, I open this door such that the wind blow in. Okay, and the wind that comes in is doesn't have high energy because the saloon hasn't high temperature. So the wind start blowing. And then the V comes here and I have high temperature here, high E here. The high energy goes out from here. The mass goes out or mass goes in. Mass goes out, bring out high energy. Mass comes in, bring cold energy because outside temperature has lower temperature. Then I transferred energy through transfer of mass through the surfaces. I didn't work on that. Why? Because this control volume has a fixed temperature, has a fixed high temperature. Okay? And the temperature was fixed. As the temperature was fixed, this term vanishes. Partial T is 0. So this doesn't work at the beginning. At the beginning, both windows and door were closed. This term was also 0. Then I open both of these two and I let the transfer of energy. So this term appears. So when mass is transferred, momentum is transferred, energy is transferred. Okay? When mass is transferred, momentum and energy are also transferred. Okay, let's go to the work. It is the first term. 126 is the first term. 127 is the second term. This book, I am using both Anderson textbook and the book of Russell and Bertin and Russell Cumming. So in the Bertin, instead of E, use it UE. I use it small e. This UE is the same as E. Okay, so work. I should correct this equation. Not this, the only thing that I should correct, I should put dot here, dot here. Why I should put a dot over W and over Q? And what does W dot mean? Yeah?
It's the rate of workout and the
Yeah.
rate of heat energy in.
What is the name of rate of work? Power. It is power. This is rate of heat transfer. Question. Why I need to put dot here? Take a look at the left. Yeah?
ET.
Yeah, because it is rate of change of energy. I write an equation which is in terms of rate on the left. So on the right, it should be also rate. What is work from physics? From physics, what is work? Yeah?
Times distance.
Exactly. F dot X. It is a dot product. Dot product. What is power? Power?
The time derivative of that,
On which one?
with respect to f,
No.
with respect to x.
X, yeah. What is X dot? What is X dot? Yeah,
Velocity?
velocity. Power is force dot velocity. The fluid. In the fluid, which forces do we have? We have three forces in total in fluid. Yeah?
Drag, viscous, or drag, lift, and
No. In terms of their origin, not their name. Yeah?
Body and surface forces,
Body and surface, there are how many surface forces?
2.
Two. What are the
Pressure,
names?
pressure and viscous.
Pressure and viscous. So F is F viscous plus F pressure plus F body dot V. Pressure force. Do you remember what was the pressure force in integral momentum equation? The pressure force in momentum equation. Do you remember what was it? It was minus P ds. Okay? What was viscous force? Tau ds. What was body force? It was a volume integral. Rho g d volume. So we need dot product velocity in all these three. So I should put a bracket dot V. So W dot is equal integral tau dot V ds minus P dot PV dot N absolute value ds plus rho g v d volume. In your book, instead of G, put FB. I put rho instead of, I put G instead of F body. And your book called this W dot viscose. Okay, there are three terms for energy. There are three forces in energy equation: viscous force, pressure work, and body work. So these are the work and heat transfer, Q. Heat transfer, we just consider the conduction in the Q dot equation, and then the energy equation becomes like equation 135. Heat transfer, the energy equation. The first term, it is the first term. Rate of energy change in the control volume. Pay attention, rho d volume is the mass multiplied by parentheses is inside the parentheses energy. The second term, energy through the control surfaces. It should be positive, but it brings it from left side to right side, so it becomes negative. The next term, heat transfer. The next term, pressure work. The next term, viscous force. The next term, W dot S. it is the external force. For example, we have a fan or something external, or shaft. It is the shaft force. The next term, body force, that's all. It is the energy equation. Okay, we can convert. You see the energy equation? The second term, this term, the second term on the second line, is a surface integral, okay? We can convert it to a volume integral, and also the pressure, we can convert it to volume integral. If we convert all the terms to volume integral, then we can ignore the, let's say, the integral and keep the differential form of this equation. I want to simplify this equation. Let me clean this board and simplify. If the flow is steady, implicit, 1D, no gravity, zero body force. Energy equation simplifies to divergence rho E plus rho to U2 multiply U plus divergence PU equal 0. I ignore it. Steady, adiabatic. Add another assumption, adiabatic. So it becomes divergence rho E plus U2 over 2 plus P multiply U equals 0. If it is 1, what is the name of P over rho? P over rho. What is the name of the parameter inside parentheses? What is the name of these two? E plus P over rho. Yeah?
Enthalpy?
Enthalpy, yeah, you are correct. It is H. So divergence of rho H plus U2 over 2 equal 0. equal divergence rho u h plus u2 over 2 equals 0. I call this A, I call this B. It is equal divergence rho u multiply h plus u2 over 2 plus rho u divergence of zero. Is there any intelligent student in this class that prove for me the first term should vanish? Who is the most intelligent? Yeah? Yeah? You raise your hand.
The first term is in row U,
Yeah, why it is 0?
you divide by 0. You multiply into the 0 side, and it just disappears.
Which term is 0? U?
If enthalpy already has the row in the denominator, then the row cancels, and then the u cancels.
No,
No,
it is
it doesn't. No, it doesn't.
no, it is very, very simple. I want to, yeah?
Divide both sides by row u. Is the other side 0? No.
No. What is this equal? Divergence rho u from continuity. It's 0. So this term vanishes. So divergence h plus u2 over 2 is 0. 1d flow d dx h plus u2 over 2 is 0. So h plus u2 over 2 is equal constant. We call this total temperature, total enthalpy, H0. So H0 is constant. Take a look, and if you have a question, ask me. Do you agree that the first term should vanish? Why?
Because it's not in the x direction.
Because it is the continuity equation. Divergence rho u is 0 from continuity equation. Okay? I consider this parameter as divergence A, B. Divergence A, B is equal to divergence A at multiply B plus divergence B multiply A. This is equal 0. Thank you. We will continue our discussion on Thursday. Thank you. Yeah. Yeah. No.
Yeah, that's what I was asking originally.
That's one for
Does it have like a